Okay, guys, today we will be discussing about the chemistry of the minerals. As you know that the food items that have too much minerals and different kinds of the minerals available and that are essentially required for the human uh, body. So first of all, we will be talking about the solubility of minerals in aqueous system. As you know that the minerals uh, that is available in the biological systems and the biological system that is containing the water in it as an essential constituents and most of the minerals and some other nutrients as well that are delivered to and metabolized by the organism in an aqueous environment. So, the availability of reactivities of minerals that depends upon solubility in the water. For example, the elemental iron that have the physiological activities in the living systems, and commonly these are insoluble in the water. So, what does it mean if that is insoluble in water? Its availability will be affected. So each food item that will have different nature of the elements, different amount of the elements, uh, but most of these elements that belongs to in groups of 1A and 7A and that exist in the foods predominantly as free ionic species. For example, we will be talking about sodium ions, potassium ions, chlorides, fluorides. So these are available in the food item in variable amount and have variable water solubility. That will depend upon the affinities of the ligands group in these minerals. So these minerals in the food item that is present as complexes and chelates. For example, when we talking about these complexes and the chelates, for example, in the cereal grains, especially in wheat, the phytate, it's a fibrous nature, phytates, that chelate most of the calcium in it. Same is the case with spinach. The calcium is chelated by oxalates in that food. So most often these minerals these are making the chelates and other complexes in the food and sometimes affecting its availability by this chelating process and affecting its availability. So the solubilities of mineral complexes and chelate may be very different from that of inorganic salts. Another example is ferric chloride that is dissolved in water. As soon as you are going to dissolve it in water, the iron will soon precipitate as ferric hydroxide. On the other hand, ferric iron chelated with citrate that is quite soluble. So citrates are the citric acid that is making availability of iron in the body. Conversely, calcium as calcium chloride is quite soluble, while calcium chelated with oxalate ions that is insoluble. So these are the two cases I have told you that is affecting the availability of these minerals to the bodies by on the property of the chelating and making the complexes. So these are the two extreme examples. Minerals and acid-base chemistry. Minerals often providing some of the properties of acid, base, or certain neutral properties as well. So much of the chemistry of the mineral element that can be best understood by applying the concepts of acid-base chemistry. Moreover, acids and bases may profoundly influence functional properties and stabilities of each food components by altering the pH of the food. Thus, acid-base chemistry is of critical importance to the food scientists. What is the concepts of this acid-base chemistry? To understand these concepts, we will recall the prostate theories of the acid and the base. These are the common theory you come across during various courses. We will recall it. Uh, a prostate acid means it's any substance capable of donating a proton, while a prostate base is any substance capable of accepting a proton. So it's based on the protons, donating the protons or accepting the protons. So many acids and bases occurs naturally in the foods. As you know, there are organic acid, just like the acetic acid, lactic acid, citric acid, malic acid, adipic acid. These are the organic acids. But in food items, some of the inorganic acids that also be used. For example, in the cola beverages, we are using the phosphoric acid. This is an inorganic type of the acid, also called a mineral acid. We are using this. It is used as an good acidulant and flavoring agent, like in the cola beverage I talked about, and some other soft drinks as well. Phosphoric acid, normally when this is used in the food item, this is a tribasic acid, means that can be completely dissociated in 3 steps, and when it dissociates, that is providing the protons. So we have talked about the Bronsted theory that is providing the protons. You can see in each step that is providing the proton. In each step that is providing the protons. So starting with the H3PO4, that it will dissociate to provide H2PO4 plus protons. Then this H2PO4 that is dissociating into HPO4 and proton. Then this HPO4 that will dissociate in the form of PO4 plus protons. So each step that is providing a proton to you. Some other mineral acids that are HCl, H2SO4 that are not used directly into the food, that are not food grades. Then as this HCl and H2SO4, these are not food grade and not added directly into the food items. For example, sulfuric acid is produced when the common leavening acid sodium aluminum sulfate is heated in the presence of water. So it's the indirect use. In the baking powder, normally this reaction that takes place. So in this form that will be used in indirect form. For example, sodium sulfate, aluminum sulfate, sodium aluminum sulfate plus moisture and heat that will give sodium sulfate, aluminum hydroxide and H2SO. So it's an indirect use. Another theories about acid and base, that is again a very renowned theory such as the Bronsted theory. This is called as the Lewis theory of acid base. Bronsted theory that talks about the protons, but this Lewis theory that talks about the electrons. So a Lewis base is an electron pair donor. By convention, Lewis acids are often represented as A and Lewis bases as B. So Lewis bases and acid that can be written as A plus B. These are the bases AB. This is the salt. So the Lewis acid base concept that is key to understanding the chemistry of the minerals in the food, and that will be based on electrons. So because metal cations present are Lewis acids and they are bound to the Lewis bases. The complex resulting from reactions between metal cations and food molecules range from metal hydrates, metal is reacting with the water molecule, to metal containing pigments. So you can see the metals are available in different forms, making the conjugate with the hydrates in the form of the hydrates, making complex with the pigments, for example, the hemoglobin and chlorophyll, making complexes with the enzyme that will be called as the metalloenzymes. So the number of Lewis bases molecule that may bind to a metal ion is more or less independent of the charge on the metal ion. This number usually referred to as coordination number. How much metals that will be combining with different parts of other materials. That will tell us about the coordination number. In the following uh, figure, you will it will more explain. So this coordination number that may range from 1 to 12, and most commonly it is 6. For example, Fe3 plus binds with 6 water molecules to form the hexacube, which takes on an octahedral geometry. So look at these examples. For example, when we're talking about the water molecule H2O, that can making the hydrates of metal with one metal ion, only one metal, one position at the combining one position at the O of the water when it is making the hydrates. This is a monodentate, combining the metal at one position only. Bidentate means a metal is combining at two sides, and this is the case in the form of oxalates. This metal COOH, or what is the oxalates? 2 times COOH. This is one COOH and this below, that is another COOH. So this metal ion that is combining at two spaces. Another bidentate example is the glycine. Glycine is an amino acid. You know that COOH, CH2, and H2. So again, this metal ion that is combining with two spaces, with O, with NH2, right? So this is the concept how much coordination is with of the mineral with other substances. So now we will be talking about the chelate effects. A chelate is a complex resulting from the combination of a metal ion and multi-dentate ligands. We have talked about the ligands, multi-dentate ligands, such that the ligand forms two or more bonds with the metal, resulting in a ring type of the structure that include the metal ion. The term chelate normally that was derived from the chelate, the Greek word for claw, to bind it. Thus, a chelating ligand must contain at least two functional groups capable of donating the electrons. Chelates stability depends upon on the several factors. So chelate have greater thermodynamic stabilities than similar complexes that are not chelate. This phenomena is normally called as the Chelate effect. Several factors that interact to the stability of the chelates. What are these factors? Ring size. These are the 5-6 factors. Ring size. Normally 5-membered unsaturated ring and 6-membered saturated rings tend to be more stable than larger or the smaller rings. Number 2, number of rings. The greater the number of rings in the chelate, the greater will be the stability. Lewis base strength, stronger Lewis bases tend to form stronger chelates. Charge of ligands, charged ligands form more stable chelates than the uncharged ligands. For example, citrate forms more stable chelates than stable citric acid. So if it is available in the citrate form, that will be making more stable chelates. Chemical environment of the donating atoms, relative strength of the metal ligand bonds that will depends upon in the following decreasing order. For example, when the oxygen as a donor, water will be more chelating power than ROH, than R2. When nitrogen as a donor, H3N will have more than RNH2 than R3N. When sulfur as a donor, R2S is more than RSH than H2S. Number 6, resonance in chelating ring. Enhanced resonance tends to increase the stability. Then number 7, steric hindrance. Large bulky ligands tend to form less stable chelates. Both complexes have two nitrogen bonds to a single copper ion, yet the stability of the ethylene diamine complex is much greater. Ethylene diamine that is a good chelating agent. Both of enthalpy and entropy contribute to the difference in the stabilities. These are again the important factors. Ammonia, ammonium dentate ligands forms one bond to copper with ethylene diamine, and bidentate ligand forms too. So these are the good example to understand how the chelating agents, for example, this we have talked about ethylene amine, it's a good chelating agent, phytate, it's a good chelating agent, oxalate, it's a good chelating agent. So these are some of the examples about the chelating agents and how they are doing their work. The difference in the entropy change is due to the change in the number of independent molecules in solution. In the first reaction, the number of molecules is equal on both sides of the equation. So the entropy change is very small. So the entropy change is very small. So look at this figure we have talked in the description. This is the, it's a cuprocine complex with the ammonia and chelated with the ethylene here, this cupid. So it's an aqueous system. You know that it's an aqueous system. It's an aqueous system that is providing the chelates. So ADTA that has much more sites to make the chelates. You can see here that have a different sites to chelate copper. That is chelating with water, OH2, NH3, OH2, NH3. So 6 hexadentate, it's a hexadentate. But here you can form the property has been changed that can combine 1, 2, 3, direct combine 1, 2, 3, 4, 5, and 6. But that is also have a ring structure. Same is the case with the EDTA. It's a good chelating agent. EDTA is hexadentate ligand. 6 that can bind at 6 points. So when it forms a chelate with a metal ion in solution, it displaces 6 water molecules from the metal. So these are the slides we have talked about today. This is the first slide that tells us phosphoric acid dissociation and complete dissociation take place in 3 steps, and each step that is providing the protons. Right? This equation tells us, this is a revision, all of this one for today's lecture. This equation tells us that if the mineral acid is used in the food, that is used in direct form. Only the organic acid and these are used in the direct form, are the phosphoric acid that can be, it's a mineral acid, phosphoric acid that can be used in the direct form. Other mineral acid is used in the indirect form, and this was the example of that. Then we talked about the binding of the minerals with some at the ligand points. We have talked about monodentate and the bidentate, tridentate, and so on. We also talked about six-dentate. So look at this one. This is binding at one side. This mineral is binding at two sides. This is also binding. This mineral is also binding at two sides. It's a bidentate, and this is binding at one side. This is a monodentate. This is a complex ligand combining its 6 points. It's a hexadentate. This is again a complex that is binding at 6 sites. It's a hexadentate again, but in this case, this is without the ring structure. This is the ring structure, and that is affecting its stability. So, thank you for today lecture. We are concluding here, and we will be coming with next lecture, and the notes are available on my website for this lecture as well as LMS system. You can download from that site. Thank you very much.